Have you ever wondered why water doesn't just freeze from the bottom of a lake up? Or how water molecules are so easily ready to break down dirt and molecules and impurities on your hands, like whenever you wash your hands in a sink? In this video, we will find out. Welcome to Side Thread, where we thread science like a needle into the real world. In this video, we will be going over water. Water and the nature of it and its properties. My name is Preston, and let's get into it. Alright, the first property, well, not really a property, but the nature of water itself is a oxygen molecule connected to two hydrogen molecules. Now, you may know this in chemistry as the upside down Mickey Mouse structure, but for the sake of biology, I'm just going to draw it like this. As you may know as well, water has a partially negative side and a partially positive side. Now, this is because of the spare electrons on the other side here, also as you may know in chemistry, but also because this bond is called a polar covalent bond. Now, the reason why is because there are two polar regions still, even after the covalent bond has happened between the two. Now, how these two connect is like this here. We have oxygen, we have hydrogen, we have negative, positive, positive. And when we introduce another water molecule around, still has the same charge, because it's a water molecule, it will be attracted to this side right here, right where the positive and negative charges meet. And this will form a hydrogen bond. These bonds are one of the strongest, and this is where water gets its properties from. Also, I wanted to explain electronegativity. If you guys haven't learned this in chemistry yet, this basically means that an element and its power to pull on electrons. So oxygen here is one of the strongest elements that has the highest electronegativity. As you may know, fluoride is the highest. And with that, there are a couple properties here in water. So we have cohesion, adhesion, high specific heat capacity, and we have less dense as a solid, and universal solvent. Alright, now let's focus on cohesion. Cohesion is water molecules that basically stick together because of water's polarity. So if you're another water molecule, as we've seen before, it both has negative, negative, positive, positive on each side. And cohesion is the tendency of water to be able to stick to another water molecule. It's as simple as that. And hydrogen bonds. that's the reason why cohesion happens, is because it's polar. Now we move on to adhesion, and this is where water has a tendency to be attracted to a different other substance with a charge as well. So here we have a wall. Let's just say that's a wall. And we have a water molecule here. This water molecule is going to have the tendency or the ability to stick onto this wall here. Now the reason why is because a wall is not going to have a completely neutral charge. It's going to have maybe positive or plus or somewhere around it. But that's the reason why water will stick to it. You see here, this negative side of water is going to be attracted to this side right here. It's not going to be like this, because positive will repel positive. So it will be moved here. And if another water molecule is here too, it'll be stuck like that. Or it could be down here as well through another hydrogen bond. Yeah, and that's basically adhesion, sticking to a different substance. Now, there is another property of water I want to cover, and it's called capillary action. Now, capillary action is most commonly demonstrated with the example of a flower. All right, a flower. Now, we want to look at the stem, also known as the xylem of the plant. Here we have, just zoom in on that part there. And right here, we draw in the stems. Now, inside of the stem is where water moves through. Basically the roots, goes up into the flower or like its branches or something. So we have water molecules in here. We have, let's just say, another water molecule there. So those water molecules are going to have the attracting nature of each other. So right here, another hydrogen bond will be created. But also because of, like, capillary action works in narrow spaces most best. And since this stem is narrow as well, it's going to move up. Now, this is also because of adhesion and cohesion, negative charges, positive, all around. So water will keep moving up. Now, the next property is a high specific heat capacity. Let's see. As you may know, water has a strong hydrogen bond between each other. Right here, hydrogen bond. Now, it usually takes 4.184 joules over grams Celsius, as you've learned in chemistry, which is it needs 4.184 joules per gram to change it by a Celsius in temperature. Now, we have, like, let's say, aluminum compared to water has a 0.897 joules per gram Celsius. Now, comparing these two, we can see that to break that bond, or not to break the bond, but to change the temperature of like the water molecule overall, you would need 4.184 joules per gram Celsius, while aluminum is 0.897, which is considerably high. Now, we can move this into the example of a lake as well. Let's go all the way to the top again. As the sun is, making it more hotter, like the air, say it's 100 degrees Celsius outside, and the water is let's say 39 degrees Celsius. Now, actually, Fahrenheit would work better here. Yeah, 39 degrees Fahrenheit. Now we can see that the water is pretty cold. But as summer, that might change to around like 7 or so, because as you may know, 4.184 joules per gram Celsius takes a long time for those bonds to break or to become hotter in temperature. If we were to say it was 0 degrees Fahrenheit out here, that's very into the freezing temperature. This 37 degrees Fahrenheit would probably move to around 34, 33. Yeah. Only because the bonds are very difficult, or the water is very difficult to have change in temperature with. And that moves us into less dense as a solid. Now, water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. And when water freezes, it aligns itself into sort of a crystalline structure here. Let's see if I could do that. It's connected here. Connected here. Actually, this should be right here. And this should be that as well. But the thing about this is it's turned 180 degrees, so there's another one right behind it. And then this here is also another water molecule into some sort of crystalline structure. And then those crystalline structures arrange into more crystal structures, and so they have more space in between them. So moving back onto our example here, yeah, it's 0 degrees Celsius outside. That's around freezing. So instead of water molecules being arranged in that crystalline structure there, it's going to be up here instead. This is because as it's getting into its shape, it's going to be instantly moving up. It's not going to be residing at the bottom. Also, if it hits a temperature change or something, then it will revert back into water for a while. Then only the ones that can successfully take the shape of the structure will be formed at the top. So all of the living organisms will be at the bottom instead of being up here, pushed by the ice. Now, water as a universal solvent, you may know that, again, water is polar. And so it really dissolves ionic and other covalent bonds pretty easily. But the thing it doesn't break down well is lipids. Lipids are nonpolar. You may learn in later sections that there is no part where water can intrude through. So let's take NaCl as an example. How do I want to do this? Well, Na here, and then chlorine here. Na would be into the positive side here. So water molecules be arranged here. And it would keep like surrounding it here. Well, chlorine is the opposite, where it will take I think it's here. Yeah, Na is positive, so it will be attracted to the more negative side of the water molecule. So let me get that real quick. Move that there, and then we have somewhat surrounding it, just as chlorine does the same, but with the positive side. And the reason why it does this is, again, it's polar, even though NaCl might be polar. There is like slight charges that water can easily break this right here, basically split them off into these structures here. Yeah, and that's what you see when you mix like a cup of salt water. So we have water here, and we have salt just up here. The salt goes here, goes down into the water, breaks down into Na and Cl, and then Na and Cl. Yeah, so it breaks down into the